Hi, this is Steve, and I want to welcome you back to another Tech Leader Talk discussion. This interview is part of the Space Tech Innovation event, where space tech leaders share the latest trends and key insights that can help grow any tech company. The event is free. You can register at spacetechinnovation.com, where you can get access to all the videos, edited transcripts, and an executive summary of each interview. Today, I'm talking with Joe Pawelski, who's the Chief Technical Officer and a co-founder of CisLunar Industries. Joe and his team at CisLunar Industries are building and operating space foundries to enable the next industrial revolution. In particular, he's working with in-space metal processing and space debris recycling. Joe has a passion for figuring out things that people say are impossible. And some of the projects that he and his team are working on include things that might seem impossible, like turning space debris and space garbage into propellants and other useful materials. And they're doing this in orbit, not on Earth. So some interesting discussions about how they test and simulate these types of projects on Earth during the design process. And Joe also talks about some rapid iteration techniques that they use when developing these types of systems. So Joe shares a lot of valuable information, and I know you're going to get some important insights that you can apply in your own tech business. So let's get to the discussion with Joe. Hi, Joe. Thanks for joining me on the podcast today.
Pleasure to be here.
Hey. So I gave a brief intro to the listeners before we started this part. Tell me a little bit, I love hearing people's stories, and audience members have told me they love it too. How did you get to where you're at today, working in the space world?
Well, like a lot of folks in the space industry, especially in new space, I had a different background than most. I started out in aerospace. I actually went to school for thermal fluids. I have a master's degree in thermal fluids engineering, which is very similar to aerospace. A lot of folks have that type of degree and they go into aerospace.
Okay.
I graduated in 2007 though, and I needed a job. So I got a job in high-speed manufacturing. I ended up building probably 100 miles worth of high-speed conveyors and different machinery that makes cans and bottles and everything you would buy in the grocery store or consumer areas at very high speeds. So some of these lines would go 3,000 cans a minute, which is no small engineering task. There's quite a challenge into doing something like that. But anyway, I always had this passion for space. I mean, I grew up, I was into space, launching model rockets. The space shuttle was on TV when I was a kid in elementary school, and I just loved it. I wanted to be an astronaut. I wanted to be a rocket scientist. All those things really fascinated me. And ironically, I was at the Coors plant, the Coors mothership plant, which is in Golden, Colorado. It's at the foothills of where Colorado School of Mines is. And I'd been following Colorado School of Mines and SpaceX, and I'd heard that Colorado School of Mines had this program in space resources. And I was just really fascinated, and I just couldn't help myself while I was down there. I was putting in a bunch of those the hard water, sparkling hard water lines for Coors actually. And I was like, hey, I just need to go up there and check out Colorado School of Mines and see what this thing is all about. And I found out that what wild timing, and all of a sudden high-speed manufacturing, how to build industrial type manufacturing capabilities on orbit and in space was a thing. And there I was, spending a career of 15 years in high-speed manufacturing with an aerospace background, and the timing just seemed perfect. So I went ahead, I ended up taking classes there, and within the first class, I wrote a paper called Lunar, which was the business case for smelting aluminum on the moon. The moon's made of very similar stuff, just the same stuff as the Earth, literally, except for no biological activity. I was connected. I kept asking, hey, who's doing metal in space? This seems like building the shovels. If we're going to build mega structures and power beaming and everything else that you'd see in Star Trek or Star Wars, depending on your persuasion, if we're going to build that stuff, we're going to need to use resources derived in space. So really fascinated by that. I kept asking questions, who does this, why, et cetera. I was finally connected with CisLunar Industries. I helped write a couple proposals. We ended up winning an SBIR to recycle space debris. And I ended up leaving my job and starting as a co-founder at CisLunar Industries. So
wow,
that's how it happened. And here we are, 3 years later.
Interesting story, and yeah, interesting. It's always fun to hear how things like that just align, and you find your purpose or whatever. It all comes together. It's like, wow, this was meant to be. So there's a lot of stuff. I was just at a recent conference, and they're talking about all kinds of different space technology, and just it's fast and a lot of things happening. What's most exciting to you about what's going on right now in the space tech world?
Well, I see. We're kind of in the golden age now, or we're approaching the golden age. So, I mean, love it or hate it, SpaceX has really paved the way for commercial space. Prior to SpaceX, there was really no approachable way to get any kind of mass on orbit. So, thanks to SpaceX, now we can get things on orbit for a lot less cost. I mean, fractions of the cost of what it used to be. And this has also spurred very healthy competition with, there's dozens of startups and then less than companies that are starting to compete with SpaceX for launch services. So this is really making access to space much easier. And it's also just exciting to see all these other startups, other people like me who always had the passion for space, who were working in industry. And now, it used to be, hey, how to create a small fortune in aerospace or in space is to start with a large fortune. Well, now we're starting to see that, hey, maybe there are fortunes to be made. So folks that spent, decided to go to industry or something more consistent are now coming back, and they're seeing lots of opportunity in space. We're getting a lot of new minds and a lot of new ways of thinking about things. And how do you actually manufacture an industrial economy in space? So that's what it really excites me.
Yeah. Okay. Yeah. There's so much to look at. So you hinted to it a little bit, but kind of what's the goal or what's the mission for your company, for CisLunar Industries?
Overall, the overarching thing is we believe that abundant resources in space are a good way to sustain humanity. So we do really think of ourselves as a sustainable kind of company. We're looking out for the Earth. Our goal is not to go wreck the solar system and turn it into a big factory. Our goal is to derive resources off world so that we can save this world for the most precious resource it has, which is a place for us to live. This is not the place where we should be strip mining materials, especially when the moon, for example, just in near CisLunar space, there's way more accessible minerals and metals and things than are easily accessible on the surface of the Earth. So it makes sense for us to exploit those. Now, granted, there's some challenges in getting out there. There's a lot of technology to develop, but I think we're well on our way to doing that.
Okay, so we're talking about some of the terms, like you talk about space debris recycling, and I know you talk about in-space manufacturing. What is that? That's new technology. I mean, it's not things we're doing today. What kinds of things are you recycling, and then what's the end product, or how is the recycled product going to get used?
Right. So I guess overwhelming when I talk about materials, the main material that CisLunar is focusing on is metal. So we want to be able to deliver metal when and wherever you want it in space. Okay. And we look at what's our input for metal. We've developed a technology to take an input and turn it into an ingot, which can be used for a lot of other downstream processes, extrusions, wire, etc. But what we take on the input, we look at stepping stones, and the first obvious thing to use is upper stages. Upper stages are relatively abundant on orbit. They typically end up in clusters, and once they're used, they're deposited in an orbit kind of for storage, and they can be there for many years, and then they can crash into each other and cause catastrophic debris events, which spread debris all over the place. And this is the kind of thing we really want to avoid. When we talk about debris and space and the risks, it's really a scenario that could occur when you have a lot of objects, one object crashes into another, it causes a chain reaction. So when we look at debris mitigation, one of the most obvious things to do is to take the largest possible contributors to debris. These are school bus size upper stages, and remove those from an area where they could run into one another. So by doing that, we can prevent a lot of these smaller debris that's really right now there's not a very effective way to remove. We have to wait for it to deorbit. So that's what we look for right now. I kind of think of it as mining. getting debris to, luckily this debris, these upper stages tend to be in clusters, and they tend to be near where other things are operating. So to gather those and move those to a place where they could be taken apart or stored and reused for something else is not as tricky as a problem as say like finding a paint chip in geo somewhere. That's going to take a different type of technology. Now we also are looking at, our feedstock might be debris. That one's nice because we can reuse something, and there's a lot of aluminum debris up there. But it could also be a fairing or something that was sent up carrying a different cargo that now we repurpose into something new. So in that way, we can kind of utilize all of the mass that's launched instead of having a large part of it just end up deorbiting and burning back up in reentry.
Yeah.
So that's kind of stepping stones. And in the future too, again, this whole thing started, or at least I got involved with CisLunar because I read this paper, Lunar. So eventually, we are looking at resources, aluminum and other metals that we would derive from the moon. A lot of times aluminum and other metals are actually the byproduct of extracting oxygen and water, which are useful. So again, it's kind of like the metal is kind of the waste byproduct. So the recycling side of this is still pretty relevant. But again, we think of it a little differently than we might think of recycling here terrestrially.
Yeah. So, and you're thinking of doing this, the recycling, like especially some of these stages and the larger pieces, doing that in orbit. You're not going to necessarily haul it to the moon and have a factory there. You do it in place or where it's at.
That's right. Yeah. So because delta V is really how we measure distances in space. So it's the amount of velocity change that is required to do an orbital transfer that's really the logistics problem here. And
because
that's
changing at speed, is that how you're kind of adjusting the altitude of the orbit?
Exactly. When all these bodies are rotating and having orbits and things like this, the simplest way to define movement is by change of velocity relative to another planetary body. So that's what and it's getting out of the gravity well of the Earth, and that takes a tremendous amount of propellant. So a lot of times the reason why debris is a problem is that the amount of propellant that it takes to get there and the logistics of getting a spacecraft out to actually take an upper stage and do something with it could cost, it's more costly than the risk that presents. So by us being able to recycle those things on orbit, number one, we can not move it very far. In many cases, we can do a delta V shift that's a lot less than deorbiting, for example, for taking to a station. And then the other really cool thing is that one of perhaps the first product that we can sell is metal propellant. So for electric propulsion, and there are some chemical propulsion things that use metal, but electric propulsion is what's interesting to us. Once you're on orbit, electric propulsion is very low thrust, but it's very high ISP. So you can get very good change in velocity with very low mass. So this is kind of how we think about fuel economy in space. Is energy isn't really part of the equation. It's a lot more how far can you get on the amount of mass that you're carrying, because you have to expel mass to move. So metal propellant is pretty efficient compared to chemical propellants. You can get a pretty good change in velocity. So you could actually use some of that debris to propel that debris into a different orbit or to a salvage yard or something like that.
Okay.
So that really solves a lot of the problems with logistics there potentially.
Yeah. So I'm not real familiar with using metal as a propellant. Is that a new technology? Does it take a different kind of engine? I mean, we hear a lot about the chemical, the hydrogen, oxygen,
Right, exactly.
kerosene mixtures, at least to get it out of the Earth's orbit. So what are the metal propellants? How does that work?
Well, so what always shocks me about space stuff and all this sort of thing is that this technology that seems very Star Trek has been around for quite a while.
Really?
50s and 60s is when I believe, if my memory serves me correctly, most of the electric propulsion kind of theories and technology was originally conceived. And really, there haven't been a huge number of breakthroughs in that. I mean, there's been more practical application types breakthroughs, like how do you get electrodes to not wear out in space? How do you make these things last a long time? But we actually, electric propulsion has been used for station keeping of geocentric satellites for for several decades now.
Oh,
And again, that technology was initially tested probably in the 50s and 60s was when it was conceived, and initially, people were doing work on this back during the Cold War era, and nuclear technology. There was a lot of really wild science that was created at that time, or figured out. So really what it is that there's more of a need for electric propulsion now because of things like Starlink. There's just way more satellites on orbit. And the problem is that Krypton is what Starlink uses, which is still pretty rare. Xenon is the other propellant that's used in electric propulsion. These are gases. So when you have, again, electric propulsion or any kind of propulsion, it's Newton's law, force equals mass times acceleration. So you can get more force by having higher mass and by having higher acceleration. So electric fields are great because you can accelerate things much faster than you would with a chemical reaction due to the nature of electromagnetics and things like this, and the speed of light, et cetera. So you can accelerate things quite rapidly, and then xenon is the heaviest gas, or really the heaviest kind of accessible gas, I guess. There's probably other radioactive gases, but xenon is the most practical inert type of thing. So that's why it's the best one for electric propulsion that we use currently. Krypton is less dense, but it's about 10 times more abundant. Now, because of the war in Ukraine, turns out that a majority of the xenon came out of the oxygen plants that were in Ukraine because of steel production. So a huge amount of production on refractory gas on oxygen, and therefore xenon and krypton has been reduced, which makes xenon more expensive than gold, pretty much. I mean, this is one of the most expensive things you can possibly buy, which is why Starlink uses krypton. Still not that great. Metal is great because it's available on orbit. I mean, it's available on the moon. Most asteroids are made out of metal. Whereas xenon, maybe there may be some to be had on Mars, but again, it's the same issue. Unless we're making oxygen at high levels by an huge air gas operation, we're not going to get any kind of large amounts of xenon or krypton, and certainly not the type that you still need. I've seen missions that have several hundred kilograms of xenon on them, which is like way more than any. It's just the cost of that is insane. And then to try to think about extracting that from in-space resources. So metal propellant, in summary, is really good because it's actually an in-space resource. It may not have quite the same ISP as xenon, but if it's abundant and can be resupplied, then the equation changes and it becomes a lot more practical.
Right.
So I'm sure there's lots. It's kind of like hydrogen, for example, is a great fuel, but it's really hard to deal with. So we use gasoline and methane and other things.
Yeah. Well, it's interesting. Well, and you're getting two big benefits. You're creating the fuel in space, so you're not having to transport it up there as you process the recycling, and you're taking dangerous items out of orbit and reducing the chance of collision, cleaning up space, or whatever the term is. It's interesting.
Yeah, that's correct. And so chemical propellants obviously have their place too. I think that that's a big paradigm shift. Is initially we were looking at human space flight. How do you get Apollo? How do you get people to the moon and through the Van Allen radiation belts before they get radiated too much? There's a lot of logistics and consideration that went into that. Whereas nowadays we're looking at how do you keep a satellite or a station on orbit for as long as possible with the resource you have. So these are different activities. You're not necessarily trying to move them quickly. I'm sure chemical propellants, the water-based propellant ecosystem, is still be very relevant. Hydrazine, all these other propellants. I think the main thing is we need to think of, hey, terrestrially we have trucks, we have trains, we have planes, we have a lot of modes of transportation for logistics, and we need all those in space as well.
Okay. So what are you envisioning as kind of a first product or a first system that you're going to put into orbit? Is it going to be focused on recycling, or are you looking at something else?
Well, we think that station keeping with metal propellant is pretty attractive.
And what do you mean by station keeping?
So if you have a refueling depot, for example, and even if you're refueling on more traditional hydrazine or liquid oxygen or something like this, more likely it's probably hydrazine is some of the initial propellants. But if you're refueling with that and you have this gas station, you have to also have engines on the gas station to keep it from drifting away.
Okay.
So unlike a gas station here on Earth where you just like have a foundation and it's going to stay there,
Yeah.
like now you got to use some of that gasoline to keep your gas station from moving away. It makes logistics a little more interesting. So we think that there's also FAA requires things to deorbit within 5 years now, unless they're controlled. So there's an opportunity here to solve two problems. Solve, what do you do with things once you're done using them? Well, yeah, you can store them on this platform. Hey, this can also be your platform to keep propellants on and everything else. And hey, look, we can take a little bit, 1 or 2% of this stuff that's been salvaged here and use that as propellant to keep this thing stationary.
Okay.
The recycling, making metal propellant is one of the easier things. I mean, nothing's easy in space, but compared to making refined alloy that would be used for like a very, an airframe on a Boeing jet or something like that, making a propellant rod is pretty rudimentary. So we think that the TRL path, I mean, we already have a very high technology readiness level on those propellant rods that we're making. We think that is something that is feasible to make within the next by 2030 or so. And we're hoping to actually sell some things by 2025 in a very limited capacity. So these are kind of like research things that we make out of payloads that are existing on the space station and convert into a wire filament or something like this that could be used for additive manufacturing. So we're actually, there's some bets out. Is the first thing we sell going to be an ingot or a propellant rod or metal filament for 3D printing? It's hard to say. It could also, I have a hunch that it might be some of the hardware that we're building to fill some of the gaps. So, this is no simple project. There's a ton of things that we have to have other people come up with, invent, and then we have to come up with ourselves. So we've invented our own induction melting furnaces and a lot of technology around this. It could very well be one of these pieces of hardware, NASA buys to melt something or weld something. So that's always, I guess that's the other thing I love about this industry is we have a lot of ideas of what the first thing is going to be, but it's pretty interesting to see what actually ends up being the thing that really everyone needs.
Yeah, when that need pops up and you're the person there to fill it. So you mentioned about all the things you have to invent, and you're creating something new that hasn't been developed in this form in the past, and you have to make it work in a hostile environment. How do you do that? What kind of techniques or what kind of things do you and your team do when you're literally creating? I mean, I know you can take some existing technologies, but a lot of this is brand new stuff. What's your approach to innovation and solving these brand new problems?
Well, first of all, I ask a lot of questions. I think that one of the advantages to, outsiders or semi-outsiders coming into space is this feeling that, hey, I definitely don't know enough to, there's always a little bit of imposter syndrome, like, oh my gosh, I'm actually gonna send this thing into space, like, man, well, and then the next thing is like, I want to make sure that I really do a good job at this and like do what so I think it's a realization that, hey, let's ask a lot of questions. And there's actually, once you get into this industry, it's a large industry with not a lot of people. So it's not hard to find, for example, we talk to everybody who has ever done anything with melting metal on orbit. And there's been a couple experiments that NASA's done on this. So we talked to every single one of them. We talked to people that have parabolic flights. We actually did our own parabolic flight. All of the engineers that built the modular space foundry parabolic flight module flew with it. And we're going to do at least one other parabolic flight, probably two more before we send this to station. So, testing it in like environments, like in zero G, is a really good way to get an idea of what's going to happen. Huge proponent of that. We do a lot of rapid iteration and applications. So, there's a real balance to this. Like, you don't want to spend a lot of time building something that is hopelessly going to not work, or that someone's already tried and hasn't been able to have work. So that's where ask a lot of questions. But then once you find out that, hey, no one's tried that yet, and there's a feasible way to do this, and hey, we can build that in a week and test it, then build it and test it, because you're going to get your results way faster than any kind of analysis. And then test it in parabolic flight and test it in thermal cycle it. It doesn't necessarily need to be TVAC. A lot of times, we're doing a foundry, so we're getting up to 1,000 degrees Celsius and down to room temperature and cycling this thing all the time. So we're constantly testing it, constantly trying to break it. We're constantly breaking things, learning how to make those things better, and pushing ourselves. Again, it's like let's get it on the parabolic flight. Well, doing that, you have to figure out what kind of power does it take? How do you not have a surge that's going to screw up the airplane? How do you bolt to the floor? These are the same kind of things that you have to do when you actually put this on station. And of course, we go through all those processes too, but it's a lot of, okay, well, what will this look like? What's the environment that we're designing it for? A lot of systems engineering, but trying to cover the unknowns, and you uncover the unknowns by testing and like, oh, hey, there's an unknown. So and a lot of times too, it doesn't have to be parabolic flight. We often just put something upside down. Does it work upside down? Does it work on the side? Does it, what happens if I drop it on the floor? Stuff like this. So it's a combination of asking a lot of questions, going down those rabbit holes that those questions take you down, trying to learn as much as you can from previous work, and then rapid iteration and building hardware. I can't stress it more that the main thing that people should do in new space companies is build hardware and test it and see what it really does.
Okay. Can you, since you're doing things that are, you had some people to talk to and get some background, but can you model and simulate this with some of the software tools that are out there? Or do you spend more time trying to figure out the model than you actually do getting results? Whereas just building a prototype or something physical to test is more valuable, or maybe that helps you model it better.
Yeah, I think I'm a proponent of both. We do both. But there's nothing like having a physical model to compare your data to. We've gotten, I've flown thermal fluids was my master. So I've modeled a ton of things. And recently on this, we had to model things to make sure we got approval for a parabolic flight. So we did a lot of stress modeling, stress to failure, seeing what would happen in a worst case scenario. But there's nothing like actually having the solid thing and sticking a bunch of weights on it to say, oh, hey, wait a minute, that assumption we made on our bolts was wrong. This is the problem with modeling. It only takes one assumption to be inaccurate to get something totally off. And so if you can do rapid application type tests, you can figure out, okay, hey, this should be at least in this magnitude, this range. And then it's much easier to get to see like, hey, this model's obviously wrong. And that's what I found. Like oftentimes these models are like clearly wrong and it's easy to catch. And then once you catch that, it's catching unknown. Oh, didn't I model those bolts wrong or whatever it was? And then you can actually get quite close, but it's having these two to work off each other, it really accelerates the process. And it really like tells you that, hey, my model I have confidence in this model, so I understand why this model is giving me the results it's giving me.
Yeah. It's interesting. So using it as a tool and I guess training the tool, training the model as you see what's happening in the real world and converging on a stronger model that I assume then that helps you on future projects and future developments.
Exactly. And you can use the model to develop the next application faster. And yeah, it's using each tool to leverage one another is really the key to this.
All right. Are you able to do a lot of this testing in your own lab, or do you have to go out to get special chambers or things like that?
We've been able to do a surprising amount of testing in our own lab. During our phase one, we used Colorado School of Mines vacuum lab, which is really cool. The same vacuum chambers in that lab were used to test moon rocks from Apollo. So we always joke that some of this dust on my hand is from the moon. Hope that's safe. So we did quite a bit of testing like that in a lab setting. Anymore, once a lot of this has to do with gravity type of testing that we're doing right now and how microgravity will affect us. So we haven't, a parabolic flight environment, obviously we don't have an airplane, we have to go rent that space. But again, there's a lot you can learn from just flipping something over. We have a hot shop. A lot of it's, high temperature refractory type materials. But also, by using these high efficiency induction heaters and everything, they're pretty small. And we're focusing our energy on pretty small melts at a given time. So, when you think of a foundry and other things, you think of like a big pit in the floor and a bunch of molten metal and people in silver suits. And yeah, that's true if you're melting sort of 100 kilograms at a time. We're melting 300 grams at a time max,
Okay.
which makes things a lot more manageable. But certainly, we have an office at Tycho Station, which is where Orbit Fab has their primary offices. They have TVAC and various test facilities. NASA Marshall Space Center is who's funding our phase 2, and they have equipment that we can utilize. And then we're also recently we're about to announce an award that we got with Colorado State University, who has a bunch of vacuum chambers for testing plasma thrusters and things like this.
Okay.
So we've been able to leverage partners to get a lot of these things. And but anyway, I surprisingly, you don't have to do as much vacuum chamber testing as you might think. Testing is very important, but it's not necessarily the activity you spend most of the time doing.
Okay. So to just move away from tech tiny bit, so you're the CTO, and I know you've got a lot of activities, you wear a lot of hats. What's your favorite part of the work that you're doing today? Favorite part of your job?
Oh man, probably my favorite part is talking to all these super smart folks. I alluded to it before. I don't consider myself the smartest person in the room normally. I work with a lot of PhDs and extremely brilliant people that, at least, in grad school, these guys always finish their tests before me and help me figure out how to do different types of math and whatever. So really, I think I'm a pretty good engineer, but I ask lots of questions, and being able to ask some of these people that I consider some of the smartest people in the world, hey, how do you do this? And when you worked on that project, how did you do it? And then they tell you. That is the coolest thing. I've had the opportunity to talk to several astronauts. Recently had an astronaut ask me how I liked the parabolic flight experience and being in 0G, which just blew my mind. To be, it's like you spent many missions flying around in this, in the shuttle. But having those opportunities and being able to share these things with people, I think, is probably the most exciting thing to me about being a CTO.
Okay. So you may be a bit like me, kind of a lifelong learner. You love learning about the new technology, and if you're in an environment like that where you're learning new things every day and learning from really bright people, that can be very rewarding.
Absolutely, and I think trying to help these folks, especially our engineers and everything, pursue their dreams and goals. All of our engineers still pinch themselves, I think, a lot. Like, I can't believe this is actually happening. Like you said that we were going to do this thing. I was like, you're crazy. And then I started doing the thing, and now we did it. And it's like, okay, yeah, no, that's how we do it. You get up and you make a goal and you just go after it. And so to see it happening and to see other people experience this with me, it's really cool.
Yeah. I was talking to somebody the other day who mentioned, they said some people refer to the fact that we're living in science fiction now from a few decades ago. But he said one of his employees had mentioned to him. He's like, no, we've gone past that. We've gone past. We're doing things that there's science fiction writers and things never envisioned.
They haven't thought of yet. No, that's what really inspires me. And I think I also think that it's like we're really doing really important work right now. I think people are really starting to get it that humanity needs space, and everyone's starting to look up and think like, hey, there is an abundant life here that we can have. So anyway, those are the things. Yep.
Okay. So there, as I've mentioned, there's all kinds of exciting stuff happening in the space world, but there are challenges, as with anything. What do you see as some of the biggest challenges that are facing the kind of space industry in general?
I'd say, overwhelmingly, the biggest challenge facing new space and entrepreneurs like myself are continuous funding sources. It's should be pretty obvious to anyone following space right now. New space VC investment is down from all-time record highs. Of course, now Space Force and DoD investment is approaching record highs. So the pendulum swings from one funding source to another. You have to be pretty savvy and have quite the network in order to ride that roller coaster. Unfortunately, the way universities and everybody have trained engineers and folks like this, rocket scientists, and traditionally was not to necessarily be business people. That's changing. It's really, CSM, for example, a lot of these professors are also entrepreneurs. You see that a lot more, Stanford and some of these other colleges kind of led the way on that. And so you see a lot more business knowledge and business thinking now in new space, which is probably the only reason anyone is successful right now, because it takes a business development hat. It takes understanding how to make products, how to make revenues, and how to raise money. From one day it's Space Force, the next day it's VC. It changed on the whims of politics and whatever people think the economy is going to be doing tomorrow.
Yep.
Space is a long game. We talk about planning in space. NASA does its road mapping every 10 years. And I was recently at one of these and I was laughing, it's like, dude, investors expect return on investment every quarter. We're talking about 10 years. This something is not lining up on the time frame here. So anyway, it's a combination of both. It's getting NASA and old space to NASA has a great new space way of thinking too. I don't want to discredit them, but it's taking kind of these old space views and timelines and maybe reducing those. Maybe it's 5 years. I'm not saying that we're gonna, realistically, we're not gonna do a lot of this stuff next year. It can't move at the space. Not yet. Yeah. Someday we can move at the pace of industry, or of terrestrial industry. But in order to get there, we need to think about how do we make 5-year investments? How do we get VCs and other groups that fund these types of things that are private to think about, what are mechanisms that can get me returns on investments that I need, and realize that this is a 5-10 year return on investment. It's starting to happen. There are a lot more VCs that are starting to play a longer game, or there's different exits now available for companies like ours, and ways for investors, private investors, to try to make a return. But anyway, I think I think that's the biggest problem. It takes lots of money. It takes a large fortune to make a small fortune in aerospace, and that paradigm is shifting. But man, to do what we're doing, we need to build. There needs to be a certain economy of scale of production in order to achieve lower production rates. This is basic economics. We need a long-term signal from DoD. Hey, how about a strategic materials reserve? Tell me what kind of metal you want and where you want it, and we'll build that. And then other people will be able to use those materials to build things on orbit. There's a lot of discussion going on right now with Congress. Congress is funding a lot of stuff in this realm, but we need more of it, and we need to make sure that whoever gets elected next 2 years doesn't just turn everything upside down and say, new path, new roadmap. We need to have a strategic focus, is I think at the end of the day, from both private and government.
Okay, that's good. Well, hopefully they will. Yeah, it's working together now to some extent, and hopefully that continues and just gets stronger.
One of the last bipartisan places left is thank goodness, which is one of the other reasons it's pretty cool.
It's interesting.
Yeah.
So what's ahead for you and the team at CisLunar for, let's say, the next year or two? Not the next quarter. We'll go on longer than that.
Yeah, well, within the next couple of weeks here, stay tuned, because we have some major wins that we'll be announcing. So we really we've been nailing our roadmap. We said that we would do the things we've done, and we've hit every single goal so far. So if we continue tracking down this roadmap, we will fly our Foundry on Space Station in 2024. We'll produce metal rods that we send back to Earth and have tested, so that we actually have some mechanical properties and know what we could actually make out of those materials on orbit. We also will be testing this metal propellant that we're making, so we can get real numbers from Colorado State University on what kind of ISPs, what kind of energies are required, so you can actually build an architecture around station keeping and transport vehicles, logistics for service craft and things like this that could be propelled with metal propellant. So these are the slow moving kind of, well, they take a while to get the speed, but they can go really far and take, you know, they could really be the backbone and the foundation of the CisLunar economy. So, you know, basic stuff, just building the foundations of this CisLunar economy. That's what we're doing the next few years. But yes, there's we've expanded our team double since the last year. And we're about to we're actually interviewing people right now to bring on at least 3 more engineers. So certainly if the things that we're doing are interesting to the listeners, and you know, metallurgy, mechatronics, chemical engineering, and electronic systems, you know, come check us out.
Okay. Along those lines, if any of the listeners do have questions or they want to get in touch with you or learn more about the current job openings, what's the best way for them to reach out?
Well, our website constantly needs updating, but www.CisLunarIndustries.com is a great way to find our contact information. LinkedIn, we're very active there as far as social media goes. You can find all of us co-founders on LinkedIn.
Okay.
And all kinds of neat stuff that we talk about. If you're in the space industry and you go to any of these conferences, we are often there on panels, walking around. We would love to talk to you.
Okay. Well, I'll get those links in the show notes so people will be able to find you and learn more about the company. This was a great discussion. I loved it. I learned a lot. So I like to learn new things every day, and I already have. Just thanks for taking your time. I know you're busy. You got a lot of things going on there. And I appreciate you taking the time to talk with me and share your knowledge and share your experience with the listeners.
Excellent, Steve. Well, I appreciate the opportunity, and yeah, see you in space.
That's my plan.
Excellent.